Hello students, welcome to series of lectures on digital speech processing. So in this video you will be able to learn the classroom discussion topic on LPC analysis, that is solution to the prediction coefficient. So in the last video we have already introduced that is linear predictive coding and also what is the basic principle of the linear predictive coding. Okay, and what are the different kind of applications also we clearly mentioned in one of the slide is that with the help of the LPC we can also store the speech signal parameters, and also we can do the speech recognition, and we can also do the speaker recognition, and so much of wide varieties of application that we clearly seen in the previous video. Okay, now this is the time where we are going to be learning the solution to the prediction coefficient. Okay, so let's get started. Alright, now this we have already seen that the basic idea of the linear prediction is that the current speech sample can be closely approximated as a linear combination of the past sample. So this is the speech signal S of n can be represented as alpha k into S of n minus k. So in this video we are able to learn what is this alpha k and what are the issues also we have clearly seen in the previous video. Okay, so to estimate the prediction coefficients, what are the issues that we may focus? Okay, the first issue is that we need to estimate this prediction coefficient directly from the speech signal. That is the first one. Okay, and the second one, we need to estimate this prediction coefficient from the short time segmentation of the speech. When I call the short time segmentation of the speech, that means we are going to be applying the windowing technique to the corresponding speech signal, and we are dividing with the help of the overlap add method. With the 50% of the overlapping, we are going to be applying each and every windows, that means rectangular window, to the corresponding signal, and we are estimating the parameters or coefficients. But what we need to do here is that so we need to estimate the prediction coefficients in such a way that we need to minimum the mean square prediction error. So that way we are going to be looking. Okay, all right. So the same thing, when you look to the second point in the slide, so the prediction coefficients which are determined by minimizing the sum of square differences between the actual speech samples and the linearly predicted ones. So normally E of n we can write is equals to the actual speech signal S of n minus the estimated, I'm calling some S cap of n like this. Okay, so this error is equals to 0 if and only if you equal this second term with the first term, then only we'll be getting the mean square error as 0. Okay, so there is some procedure we need to adopt in order to compute the minimum mean square error. Okay, so that means first we have identified what is an error signal. Now we need to establish a relation between the actual speech signal and then the prediction signal that you are going to be applying. Alright, so this also we clearly mentioned in the previous video that so we'll be having the impulse train generator from where the sequences of impulse pulses you'll be getting. Okay, if that is voice or unvoiced sequentially. So if that is an unvoiced, that is a random noise generator from where we are going to be seeing, and here multiplying the gain of that, and that can be directly given to the time varying digital filter. Okay, so this is a very important for us, h of z, and from where the vocal tract parameter we need to estimate. Okay, so that is a complete model of the speech production. This also we clearly seen, h of z is a complete model of the speech transfer function, g of z, v of z into r of z. Now these many methods will be having, we clearly seen that covariance method and the autocorrelation methods are only these two methods we will be having in our syllabus, and the rest of the methods, whatever the method that you are seeing from this slide, which are not there in your syllabus. Right, so what is the solution for prediction coefficient alpha k? Okay, so first what we need to do is that we are going to be computing the energy of a error signal, because we already know what is an error signal. Error signal E of n is given by S of n minus S cap of n, where S of n is the actual speech, X cap of n is nothing but the predicted speech signal. Now when you apply the short time average prediction squared error, which is defined as normal energy, okay, En equal to summation m En square of m, that can be given as summation Sn of m minus Sn cap of m whole square. Okay, so when you do like that, so you'll be getting what? Sn of m minus, so this Sn cap of m nothing but sigma k equal to 1 to p. This is the basic principle of the LPC that we have already know, the mathematical expression with reference to that. So alpha k into Sn of m minus k whole square. So what we are doing, we are selecting the segmentation of a speech. Okay, we are applying the window technique and we have taken only the segmentation of the speech. Okay, so in the vicinity of the sample value of n. So the key issue that is to resolve is the range of m for summation. That is very important, because normally we are going to be looking here in generalized manner, because when you take the summation value from m equal to minus infinite to infinite, the complete set of values that we are taking, but that is not our interest. But what is our interest? We need to apply the window only specific interval. We need to fix the interval of the summation. So in order to fix the interval of the summation, we are introducing the two methods, that is covariance and then autocorrelation. So that way you need to understand. Okay, so what is the key issue here is that to resolve the range value of m. So that we are going to be discussing. Alright, so when it comes to the solution, what we know that we have already computed what is the error, and also we have taken the energy of that, and now we can find the values of alpha k that minimize En by setting this relation. So dou by dou alpha I En is equals to 0. So with respect to alpha I, which is a variable, and we are equating this equal to 0. So what we are doing here, we have already computed the energy of the error sequence. Now we are going to be taking the first derivative with respect to alpha with some other variable. Then when you equate that equal to 0, we will be having the solution for the prediction coefficient. Now let's get C. So in what way we are going to be getting the solution for this? Now which will give the two set of the equations, right? So we'll be having, minus 2 summation. It's just like when you expand the a minus b whole square. When you take the derivative of a minus b whole square, first it becomes 2 into a minus b, and then we are independently doing the derivative of the variable. So that way, the same way we are going to be doing here. So where alpha k are the values of alpha k cap we have taken here. Okay, so that minimizes the En. So prediction error is orthogonal to the signal for the delays I of 1 to p. So for all the relations, whatever we need to see, so I is varying from 1 to p. Here also I is varying from 1 to p. Now we can find the values of alpha k that minimize by setting dou En by dou alpha equal to 0. So this is the way. It is a simple mathematical derivation, that's all. It is nothing like that. It is very simple derivation. But here the term whatever s of m minus I that you are going to be seeing, that we are going to be equating equal to minus dou by dou alpha I into summation. So this is nothing but the delayed version of the speech signal only. Okay, so in place of that, when you substitute and when you're getting the value like this, so that we are calling as phi n of I comma k. Okay, so it is an autocorrelation only. So autocorrelation nothing but what? The set of sequence when you consider Sn of m minus I into Sn of m minus k. Okay, where I is varying from 1 to p, and k is also varying from 1 to p. Okay, so like that we'll be easily establish a relation between the phi n of I comma k. With respect to this equation, we have chosen this complete term as nothing but phi n of I comma k. But with respect to this, if this is phi n of I comma k, because there is no k equal to 0, can I call this as phi n of I comma 0? Yes. So the left hand side term of the equation is referred to phi n of I comma 0. So in the right hand side of the term we'll be having, in place of this we are writing directly phi n of I comma k. Okay, now what is the relation that we have got? So phi n of I comma 0 equal to summation k starts from 1 to p alpha k phi n of I comma k. So which leads to set of p equations in p unknowns, and that can be solved in an efficient manner for the alpha k. And we can also express this equation in the matrix form. Okay, that also we can see in the next slide. So this is the relation we need to understand, because when you apply covariance method or when you apply the autocorrelation method, So there we are going to be utilizing the same equation that you are going to be seeing from equation number 1 and 2. So these two equations are very important for us to understand covariance method and also autocorrelation method. The same thing, whatever the thing that we have already seen in the previous slide, I have given. Right. So when you represent the same phi n of I comma k, let me write that phi n of I comma k is equals to what you will be getting. It is phi n of I comma 0, not k. Phi n of I comma 0 equal to alpha k. This is a column vector into the row matrix and column matrix will be having phi n of I comma k. Okay, you can easily represent the matrix form like this. When you substitute I equal to 1, k equal to 1, this is the way. This is a p by p matrix will be getting. Okay, so this is a p by p matrix, and this is a column matrix, and this is also column matrix. But what is our agenda? Now we need to apply one method in such a way that we need to compute all the prediction coefficient values starting from alpha 1 to alpha p. If I take p equal to 4 for instance, we need to compute the values alpha 1 to alpha 4. That's all. So that is the way how we are going to be estimating the current sample by taking the previous sample's knowledge. Thank you students. Thank you for watching this video.